Hello, I hope you are doing great. In the last lecture, we understood what are the challenges of the distributed storage system. Can you just remember what are the challenges? One is how do you manage the data node failure? The second one is how do you manage the name node failure? Having understood the challenges, how do we really take care of those challenges? Let us try to understand how do we tackle the data node failure as a part of this lecture. We understood when we have a data node failure, for let us say our file is 1 GB, that is split into 8 blocks and it is stored across 4 data nodes. As we understand, data nodes are nothing but the systems. Each of the data node is holding 2 of the blocks. You can see there are 8 blocks here. As we understood, what if the whole data node gets corrupted? The system itself crashes. What will happen? We are losing the data. We'll not get the data in entirety. How do we really handle the data node failure? We need to define a replication factor. What is really replication factor? Replication factor is nothing but how many times a particular data need to be replicated. What do we mean by replication? Replication is nothing but, for example, we have block 1 and block 2 in data node 1. If we store block 1 and block 2 only in data node 1, then it is stored only once. Instead of storing the block 1 and block 2 in the data node 1, if you go to store the data in another data node also, that is called as a data is being replicated. We are making a copy of it. In case if this gets lost, at least we have this particular copy. Because as we know, system failure is the norm in case of commodity hardware. In that case, if a particular data node crashes or it gets corrupted, so then we need to have a way of retrieving all of our data, right? That is where replication comes into picture. Replication means make a copy of same data one more time, or whatever the times your replication factor is being set. Now we are replicating the blocks. It wouldn't suffice only replicating the blocks. We also need to ensure that we're replicating the blocks in different locations. What do I mean by that is, let us say you are replicating block 1 and block 2 and you are replicating the same thing in data node 1. It doesn't make sense, because if the data node crashes, the whole data is again gone. So what we need to do is we have to replicate the blocks in a different data nodes, in a different location, so that our data is safe even though one of the data node crashes. That is how we are tackling the data node failure. As we know, in data node we have a data, we have a actual chapters. If you consider the whole book as a data, we'll have a name node as a table of contents, and actual chapters are data nodes. In case if the data node fails, we are trying to tackle that by defining a replication factor. When you say defining a replication factor, we are replicating the blocks. We are making the copies of the blocks depending upon the replication factor. We'll talk about replication factor in some time. One more important thing is the replica locations are also stored in the name node. As we understood in our previous lecture, we want to read data in a data node. Obviously, we need to go through name node. That is the address where all the data is stored. It is where the metadata is stored. If we replicate the data, if you make a copies of the data, if you are not updating those locations in name node, again it is useless, right? We also need to ensure that replica locations are also stored in the name node. For example, now file 1 block 1 in data node 1, file 1 block 2 is data node 1, and we do have the same block 1 and block 2 stored in data node 2. The framework itself ensures that replica locations are also stored in the name node. So that way, whenever we request for a reading of the data, we'll also get to know the where exactly the data is stored by referring the name node. and will go to that particular place and read the data and come back in terms of how you really read the data. Having understood how do we really tackle the data node failure? That is by defining the replication factor by replicating the data and storing the data in different data nodes. How do we really choose the replica locations? That is one of the very important aspect to be considered. We need to choose the replica locations by maximizing the redundancy and minimizing the write bandwidth. What are these? As we know, redundancy is nothing but having more replicas of a same data. If you have 2 copies of the data, then you are safe. If you have 3 copies, you are much more safer, right? That means to say that you need to maximize the redundancy in terms of number of replicas and also storing that in a different locations rather than in the same location. That is how you maximize the redundancy. But coming to the minimizing the write bandwidth, let us say you are in San Francisco and you send a 1 GB of email to one of your friend who is in Bangalore. Do you think it takes the same amount of time as that of sending a 1 KB of data from San Francisco to Bangalore? Not really. 1 KB of data gets sent to the Bangalore location as soon as possible within a fraction of a second. But when you are trying to send a 1 GB of data from San Francisco to Bangalore, then it takes more. We wouldn't realize that, but it happens whenever you are sending the more amount of data for a faraway location, then it takes more time rather than sending the same amount of data for a location which is near to your location. We also need to ensure that whenever we are replicating, we are minimizing the write bandwidth. We'll see that in bit more detail. Assuming that we have servers in a data center. For the discussion purpose, let us assume that we have 3 racks: rack 1, rack 2, and rack 3. We have these servers in these data centers. Now, if we were to store the data considering the replication, assuming that let us take only one block for the discussion purpose. So how can we really go and store the one block across these 3 racks to maximize the redundancy? That is something which we have to think through. To ensure that we are taking care of the data node failure. When I say data node failure, a system crashing, one of the CPU crashing, so that whatever the data which is stored in that particular system can be recovered. One important thing is make replicas. Second important thing is store the replicas in a different locations rather than in a one location. Those are the 2 important aspects. Now, since we have 3 racks, the ideal way of storing the data is store the data in rack 1. I'm talking about only one block here. This is the block. The same block is stored here and here. As we discussed, we are replicating the data and also we're ensuring that we are storing the data in a faraway locations rather than storing in a same rack. But when we want to store the data in faraway locations, that will really help us to minimize the loss of the data. I mean, in case if there is any loss of the data, we'll be able to quickly recover the data from a rack 2 or rack 3. What happens is in maximum redundancy, we'll store the replicas far away on different nodes. That is what happens in the maximum redundancy. But in case of minimizing the write bandwidth, as we know, more farther the locations will be incurring more resources and time. We are taking more bandwidth to store the replicas. This is what happens when we need to minimize the write bandwidth. Now, how do we really take care of this minimizing the write bandwidth? What happens is there is a node that runs the replication pipeline in a particular rack. What it does is it chooses a location for the first replica. In this case, let us say this is the first replica location. When I say replica, it's a block of a entire data. In our case, remember, we split the 1 GB text file into 8 blocks. Consider one of the block in that particular file. This node chooses the location for the first replica. In this case, this is the location. Next, what happens is the data is forwarded from here to the next replica location. Then this data is forwarded further to the next replica location. This is how the storage of the replicas happens. First, the replica is chosen here in a random manner, and then that will be forwarded to the next rack. and then it will be forwarded to the next rack. As we discussed, forwarding from one rack to another rack incurs time and resources. We can call it as a bandwidth, because we are not talking about a small amount of 1 KB or 1 MB, 250 MB of data. We are talking about GBs of data here, because as we know, whole of big data ecosystem, we are talking about potentially storing GBs, TBs, zettabytes of data, right? When we are trying to store the data and we are trying to replicate the data and store that in a different rack, forwarding from one rack to another rack takes a lot of time, and also it incurs large amount of bandwidth. Now we understood two aspects. One is we have to maximize the redundancy. At the same time, we have to minimize the write bandwidth. We cannot only look at one aspect, like only will go ahead and maximize the redundancy. At the same time, we have to take care of the write bandwidth also, because we are not talking about storing a less amount of data. Let me repeat, we are talking about storing a more amount of data. When we talk about storing a more amount of data, what will happen is even forwarding from one rack to another rack takes lot of time, because it incurs more write bandwidth. How do we really balance both these needs? One is maximizing the redundancy. Second thing is minimizing the write bandwidth. The way we can tackle this is, first location chosen at a random. This is the first location. Then the second location has to be on a different track, because if you store the data in a same rack, what happens is if this whole rack crashed, the whole rack, then again the data is lost. First location is chosen at random. Second location has to be on a different track. That is mandatory thing. And how about the third location? Just to minimize the write bandwidth, what we can do is we can take the third replica and place it on the same rack, but on a different data node. Instead of placing in a same data node, we can choose a same rack but place the replica on a different data node. So that way you are replicating the data also, and it is placed in a different data node. At the same time, you are trying to minimize the write bandwidth as much as possible. In a way, reduces the interact traffic and improves the write performance. Now that we balanced both the needs, one is maximizing the redundancy. The second thing is minimizing the write bandwidth. Whenever we send the read request to read the data, which will go through the name node and it will come to the data node and try to read the data from there. How it happens is the read operations are always sent to the rack closest to the client. Let us assume that we have our data centers. One is having a 3 racks in the same data center. The second thing is we have 3 data centers. One is in San Francisco, second thing is in Seattle, the third one is in London. If a person is trying to access the data who is near to the Seattle, read request will go to the Seattle data center. Read operations are always sent to the rack closest to the client, so that amount of time taken to read the data from the data nodes is as minimal as possible. That is one more important aspect. As we understood, to tackle the data node failure, we need to define a replication factor. Replication factor is nothing but how many times the data need to be replicated. The way we can configure that is, we can configure that in a XML file in HDFS. It will be found in the wherever Hadoop is installed, and we need to configure the replication factor in HDFS-site.xml. We'll see that in action. Let me go ahead and see where exactly our Hadoop folder is. In this case, our Hadoop folder is there in etc folder. Let me go there. Go. I'm going to Hadoop. So ls, we have a con. We can see conf folder here. Okay, we can get into that. If you go and see here, we'll see important XML files here. One of the important XML file is htfs-site.xml. Let us go and see what is there in this. Oh, there comes the replication factor. Here, as we discussed, this is where the replication factor is set up. This is a HDFS site.xml where we had to set the replication factor. We have set a replication factor as a 1 here because this is a pseudo distributed application, wherein that we are trying to run both the name node and data node from the same application. That is the reason we have 1 as a replication. This is where we have to go and set the replication factor. Then the question may arise, what should be the ideal replication factor? It depends on the project. Let us say you are working in a retail project. All the data is important, but it is not that the moment the data is lost, one of the life is at stake. Default replication factor is 3, that we can go ahead with the default replication in case of a retail project. I'm just taking an example, depends on the project. If you are trying to store the data of avionics data, like aircraft data, even the small error may end up in a loss of a life. In that case, you may want to define the replication factor as a 4, so that each copy of the data is stored 4 times. Defining the replication factor depends on the project which you are in. We can go ahead and define the replication factor in a HDFS site.xml. In a fully distributed mode, the default replication factor is 3. As I updated, it depends on project to project. If you want to have more copies of the same data, you can go and update it. But in pseudo distributed, we'll have only 1. That completes the how do you tackle data node failure. We discussed we can tackle the data node failure by defining the replication factor. The default replication factor is 3. That means to say that we are storing the same block 3 times, and that should be stored in a different racks. And also we need to balance between maximizing the redundancy and minimizing the write bandwidth. Thank you.